Hi everyone, so today we'll be solving Leetcode question 797, all paths from source to target. So let's see what the question has to say. So according to the question, we are given an directed acyclic graph. By acyclic you mean that you cannot have cycles in the graph, and there are total n nodes, and they are labeled as labeled from 0 to n minus 1. So we have to find all the possible paths from the node 0, that is the source, and to the node n minus 1, that will be our destination. And we have to actually print the paths in which we'll travel to reach the destination from the source, and we can print them in any order. As you can see that any order is acceptable. So if you see this example, the source here is 0 and n minus 1, that is 3 here, because total number of nodes are 4. So we have to print all paths from 0 to 3 in this case. So we can print them in any order. So now we'll see that how can we reach and travel to every path from source to destination. So I hope the question is clear. Now to see that how we are going to work on this question, so the algorithm that we are going to use is called DFS. If you are familiar with graph algorithms, that is going to be a great headshot for you to solve this question. So the approach that we're going to use here is, as I mentioned, DFS. That is going to be a very simple DFS, which you may have used in earlier simple questions also. So here we go. Like you can see that we have a start node. So this is our source node, and in this case we have 5 nodes, right? So n minus 1, that is the destination, will be the 4th node. So this is our destination node. Now we know that we have to travel from 0 to 4 and store all the paths and return it in the form of an answer. So my way of doing it will be that we'll start with a simple DFS. So we start with 0 because it's the source node, and the source node is never going to change, right? So we have always to start from 0. That is what we have been given in the question. So I'll start my DFS from the source node 0, and I'll see that where are all the paths that I can travel from 0, and then like if I come to 1, then from 1, how many nodes can I travel from 1. So in this way we'll do the normal DFS. So before going into the depth of how the algorithm is going to work, so first of all I would like to tell you that the important storage that we are going to use over here, the vector that you can see over here is going to be a storage, and this is going to be a kind of a temporary storage to store the current path on which we are traveling, right? So this is basically a path vector, and it will, suppose if we are traveling from 0 to 4, so we'll store the path that is 0 and 4 in the vector so that we can push it to our answer vector once we reach our destination. So this is a temporary path vector. So now let's start how the DFS will actually work. As you can see that we have been given an input in the form of a graph vector. So basically if you see it carefully, it's kind of an adjacency list that you have been given already in the input form, right? So like you can see that this is the 0, if like it's like the 0th node over here, and you can see all the neighbors that you can travel from 0, like you can reach 4, 3 and 1. So that's what it is given over here. Similarly, this is for 0, this is for 1, this is for 2, and this is for 3, and this is for 4. So the 4th one is empty because 4 is a destination node, right? So this is the adjacency list that we have been given. So now we have to look how can we traverse it, just so that we get all our paths according to what is being asked in the question. So let's start from 0. So now when we start from 0, we look upon the adjacency list that we have. So we see that like the first neighbor to 0 is given 4 over here, right? So we look the adjacency list and see that first we can go to 4 from 0. So we'll do a call to the neighbor of 0, that is to the 4. So before making any calls, our first step should be so since I started my DFS from 0, so now when I am on 0, so my first step should be to push the node I am currently standing on into my path vector so that I can track the current path I am going to follow. So when I was on source node, I started from the source node, so my initial work is to push it into the path vector. Now I am going to call my first neighbor from the adjacency list that we have. So we call upon 4. So we go to the 4th node, right? So our first work, as I said, is to push the node that we currently are on. So now we are on 4, so we are going to push it into the vector. So our temporary path vector has 0 and 4 right now in its state. Now after pushing it, you need to check that the node that you're currently standing on, is it your destination node or not? So in this case, we see that yes, 4 is a destination node. So that means that we have reached the destination, and now we have to store the path from which we have come to this destination, right? So the path that I'm talking about is here, right? So we just stored it when we were traveling to 4. So we now have the path. So once you reach the destination node, you're gonna push the contents of this temporary path vector into the answer vector that you are going to make, so that you get all the paths. So now the answer vector will basically be a vector of vector, as you can see the format of the output. So now in the answer vector you have 0, 4, right? So your first path is done. But since it is not necessary that you only have one path, right? So we need to go back and find that are there any other paths possible to reach 4 or not. So now if you see the adjacent, now since it was the destination, so its adjacency list is empty. So now we need to go one step backwards and see that are there any more paths that exist to reach 4 or not. So now when you go one step backward, so you must be familiar with how recursion works, right? So when you go one step backward, so like since I have not passed the path matrix, so the path vector by reference, so its contents are going to be changed as changed back to the state how it was before the call was made. So since you have backtracked to the previous state that in which we are standing on node 0, so your path matrix will have the contents that were originally there when you were standing on 0. So when we were standing on 0, we didn't have 4 there, right? So currently we have 0. Now from 0, you see the adjacency list, we have traveled to 4. Now our way is to go to node 3 to find out all of the paths. So now we are going to make a call to 3. Now we are on 3, so our first work is to push 3 in there. And from 3, we are again going to see that is it our destination? No, it's not. So we are going to look to our adjacency list of 3. So the list of 3 only has 4 as its neighbor, so we can only go to 4. So we are going to make call to 4. Now first work is to push 4 because we are now on node 4, and then we check that is this the destination? Yes, it is my destination. So the work we did previously was to push all the contents that you have in the path matrix to your answer path vector to your answer vector. So now you have 0, 3 and 4 over here. Okay, so your second path has also been traveled successfully. Now your work is to go one step back and see that are there any other paths that can make us reach 4. So you go back from here and then you come to 3 and see that in 3's adjacency list we only had one neighbor, that is 4, and we have already traveled to that node, right? So we don't have any other node to travel, so we are going to backtrack from here also. So as I'm backtracking, we also need to change the state of the path vector, right? So we are back again on 0. So now from 0 we see that we have traveled 4 and we have traveled to 3. Now we have to travel to 1, right? So now we are going to make a call to 1. Once we make a call to 1, we are going to write it into our path vector that we have over here. Now we are on 1. So 1 is not a final destination, right? So we have to see 1's adjacency list, and you see 1 has 3 neighbors. So we'll call upon the first neighbor, that is 3 over here, right? So we'll go to 3. Now 1 will make a call to 3. Now once you're on 3, you again first of all push it into the path vector that we have, and then you see that it is not a destination that we had in the question, right? So we'll again look to the 3's adjacency list, and then you see you have 4 here. So you'll again make a call to 4. Now you are on 4, so you push 4 again, and then you see it's a destination. So your work is to put push this path again. So you will have 0, then 1, then 3, and then 4 now in the answer vector. So you have explored 3 paths. Now you'll do the same step again. You are on 4, so you'll go one step back and see if any other paths can be made to reach 4. So from 3 we cannot go to any other neighbors, so we again backtrack by one step. Now backtrack here to 1, right? So now we are on 1. Now we are on 1, so we see the adjacency list of 1. We have traveled to 3. Now we have 2 more neighbors to go. So we'll go to the first one over here, that is node 2. So now we make a call to node 2. So okay, so first of all we need to make our path vector correct. Since we are on 1, so we will have contents till the state when we were on 1. So from 1 we have made a call to 2, right? So we come to 2 now. So you push 2 over here. So you push 2 over here, and then you see that from 2 you have only one node to visit. So you make a call to 3 then. So from 2 you can go to 3. So you will make a call to 3, and then you push 3 in here, right? But since now 3 is also not a destination node, so we'll again look 3, and then you can see that we can reach 4 from 3. So when you reach 4, so you'll again push 4 here, and then you see 4 is a destination. So you have another path to reach 4. So that will be 0, 1, 2, 3, and 4. Right, so we have 4 paths till now. We have explored 4 paths. So now we'll go one step back. We come to 3, and then you see you cannot go anywhere else. So you backtrack one more step, and then you come to 2. From 2 also you only have one node to visit. So we have already visited that. So let's go back one more step, and then you come back again to 1. So let's first make our paths vector correct. Since we are on 1, we have to make it look right. So now we are on 1. So on 1 we have only one more neighbor left to traverse. We have traversed 3 and 2, right? So we can also go to 4 from 1 directly. So now we'll make a call to 4, and then once we are on 4 we need to push it over here, and then you see 4 is the destination. So you are going to push the contents of this path again into your answer. So we have 0, 1, and 4 over here, right? So this is a destination, so we'll backtrack one step and see if other path exists. Now we are on 1, and we have successfully traversed all the neighbors of 1 that we could. So you have nowhere else to go from 1. So you'll backtrack one more step, and then you reach back to 0. So let's make our path matrix, right? Now you are back to 0. So from 0 we'll see that in 0 also we have traversed all our nodes that we could, right? So now you have no place to go. So that is where your DFS comes to an end, and this simple backtracking technique, using this simple backtracking technique, we were able to actually find out all the paths that we could travel to go from 0 to 4. So in this case there are total 5 paths. You can see in the answer we can return them in any order. So we have 0, 4, 0, 3, 4, 0, 1, 3, 4, 0, 1, 2, 3, 4, and 0, 1, 4. So this is what your answer is going to look like. I hope the algorithm walkthrough is clear. So let's go ahead and write the code. So initially, as I mentioned, that the return type of this function is vector of vector. That is going to be your answer. So let's create a vector of vector to store our answer. And I also mentioned that we will be needing a temporary path vector. So we'll name it as path, right? We'll pass it into the function that we'll call over here. So the next work is to actually call our DFS, right? So we'll we'll create a function named DFS. So we'll see what all do we have to pass. So first of all, the graph vector of vector, that is basically our adjacency list that we have been given here. So we'll pass it, and afterwards we need to pass the path vector, the answer vector, and then we need to pass our source. So our source is 0, right? So every time it is going to be 0, so we will send 0, and a destination every time is going to be here, right? 3 n minus 1. So we will do graph dot size -1. So yeah, so that's the n minus 1. So now we put a semicolon, and now you have to write the DFS function that we mentioned. So let's write the DFS function. So first of all, the function has to take certain parameters. You have graph, and then you need to take this path. So please note carefully that I am not passing path by reference because I need state to change according to the recursion state that we are in. If you want to pass it by reference, then you need to use you need to pop the elements also at the end of the recursion. So I don't want to get into those complexities, so it's easier to do it without by passing it by reference. So let's also pass our answer. Right, so this answer has to be passed by reference because every the change that is being reflected in it at every recursion needs to be reflected in the final answer. So we are passing it by reference, and then we have source, and then we have destination, right? We have got them all. Now let's start the call. As I said, that our first step when we come to any node is to put push it back into our path vector. So we push the source. So the current node that you are on is basically going to be the source, right? So not every time it is going to be the source. So we are going to change the source every time. You'll see how it works. So initially you push 0, right? So you come over here, and then our next step was to check that is the current node that you are on is our destination or not. So you see, if source equals to destination, so we have two things to do over here. That is to push back the contents of our path vector into our answer vector, and the second thing is to return, right? Okay, we didn't mention the return type. It is going to be void over here. So what if the source, like if we have not reached the destination? So our work is to traverse through let's say I traverse through the adjacency list of that node that you're currently in, and then when you traverse, you have to make a DFS call again. So we have to pass graph, then path, then answer, then yeah. So now at the place of source, so source is basically you can say every time you come on a node, so the node on which you are currently on is representing the source. We could also name it as node. If you want, you can do that. Just understand the logic behind it. So we are going to travel to its neighbor, right? So the source will have to change. So it will be I. So I will be like the neighbor of the node that we are on. So we have to pass it instead of source, and then we pass destination because destination is not going to change, and then that's it. Yeah, so your DFS function is complete, and in the end you need to return the answer so that yeah, you're done with it. So now let's try running the code. You can see this passed. So now let's try submitting it. Right, so we have successfully solved this question. I hope the concepts were clear, and if you guys have any doubts or any improvements that you want as a suggestion to be suggested, you guys are free to welcome in the comments. Thank you for seeing the video. Bye bye.